My name is Bielkiewicz, and I'm going to talk to y'all today about Crossflow cooling towers. So first off, what are they? They're essentially large heat exchangers. They're used for cooling buildings, mechanical devices, whatever else. You can identify them by this picture here. There's these large dome-shaped things on top of buildings. Those are cooling towers. But what they do is they remove heat from water and put it back into the atmosphere through evaporation. There's many different types. This is going to focus purely on Crossflow. Moving on to the background, the late 1800s, around 1885, was the first cooling tower, and they were used as steam engine condensers. In 1918, the hyperbolic cooling tower was developed. It's a hyperboloid shape, and they're efficient, and I noticed it immediately because they're still used for a lot of plants and systems today. In the 1950s was a fan, which improved the efficiency. And in the 90s was a computer controlled system. So basically, you can manually set the flow rate in different conditions to what you actually want it to be. So, how do they work? Heated water comes through the top here. It runs downward through a piping network, which is then exposed to air. And the air is brought into the tower through a fan and motor. Whenever they meet, a small portion of that water is evaporated, and as you can see, that red arrow going up, that's the cooling tower top. It's released into the atmosphere from there. So that's what you see coming out of the cooling tower. It's that moist air coming out. What is the main process we're trying to do here? The hot water comes in, interacts with the air, and then collects in a cold water basin at the bottom, and then runs back through to go through the system, and then the cycle just repeats itself. So what are you trying to do is you're trying to cool the water. So you want that water to cool off so it can eventually go cool off the rest of the buildings or systems it needs to. I'm going to leave this up here a second before I explain it. Okay, so hot water, after it cools off the devices, it heats up, it comes in from the top, it flows downward while dry air comes in from the side. They interact, they fill up in those fill basins in the collection basin at the bottom. The cold water runs out, which then obviously cycles back through the system. But as it collects, it in the middle is where the small portions of air is evaporated and goes through the top. So this is the best picture and animation I could find, and it really made sense to me. Here's another one, just another visual. So the hot water comes in from the top, just re-explaining it. The dry air comes in from the side, they interact. That moist air comes up from the top of the tower. The cold water basin collects the cooling and cold water and then runs back through. So specifically what makes Crossflow different than other different types is that the hot water comes in from the top and runs downward while the air cuts across it horizontally. That's what separates it from counterflow or any other type for that matter. And the only downside is the motor and fan that does bring the air, the dry air into it. If they're not protected, they can freeze, which I'm going to get into freezing in a second because that's one of the big keys and prevention things that you have to look out for. So some of the other considerations I'm going to look into right now are starting with drift. Drift are aerosols, droplets of water that you don't want. And as you only want air coming out of the cooling tower, sometimes you'll get droplets of water. It can cause erosion, corrosion, can damage equipment around it. So this isn't good, so you want to prevent it. So the main way to do this is a drift eliminator, and I have a picture here. It's a cellular drift eliminator, and what they do is they collect those droplets and then they drain back into the wet section. Another big consideration is splash out. So, nothing's ideal, and obviously if that much water is running through at however many gallons per minute on the system, water is going to come out the side sometimes, and one of the big ways to prevent this is a splash out reducer. I've got a picture here. It's basically these 45-degree slants on the building, so when water does splash out, it catches it. so it doesn't go on the ground. And if it freezes over, it can catch it. So it's a very big safety mechanism. And also are air inlet louvers. And these are basically like the filters you put on your air conditioning, and they prevent sunlight damage, vibration, noise, and also freezing. So those are the two biggest things to prevent splash out. So going into freeze prevention, so you want to prevent. It can happen, which if it happens, you have to turn off the water, heat it up, and then slowly turn the water back on to see if there's any cracks. But I'm going to talk about how you prevent it. First is just performing regular visual and functional inspections. Next is maintaining a high heat load. So obviously freezing is whenever the temperature gets too low. So you want the temperature to remain high, and that's maintained by keeping a high heat load. You want to sustain the flow rate. So a good way I think about this is a lot of times when it gets cold in your house, you're told to drip your faucets at night because that keeps the flow going through so nothing freezes. And that's the same way I think about this. You want to sustain the flow rate. And lastly, you want to prevent freezing in that cold water basin, which is susceptible to freezing because it's the coolest water and that's where it collects. And the way you do this is immersion heaters. They're submerged in the actual water. They're 100% efficient because they're active heating, and they keep the temperature above that minimum standard you want. And the reason they are 100% efficient is because they are electric. And moving on to this diagram, you can see the bottom is that cold water basin where the splash fill and the water is drawn and goes into. And the reason you want that water to go directly into the cold water basin and control the temperature there is because you can have a variable flow system, so you can control the flow rate going into it, and the pan heater can control the heat dissipation. And I'm going to get more into that later on. Next, I have a picture of a nozzle, and for Crossflow, they're usually these spiral target nozzles. And of note, you can have them at low height and high height. If there's a low fill, the lowest nozzle is going to be filled and touch the water, whereas if there's a high flow rate, both the high and the low elevation nozzles will be filled. Also, there's a three-way bypass valve which controls if the water can go to the hot water basin, cold water basin, and it basically directs that. So it's really important for controlling the system. Wet bulb temperature is different from dry bulb temperature because dry bulb is just like looking at a thermometer, whereas wet bulb takes the ambient temperature and the humidity. So for example, that's why Louisiana is so much hotter and seems so much hotter than other places at the same temperature because of the humidity. Cooling towers use evaporation for cooling, and this is important to understand because there is less evaporative cooling when the humidity is higher. So now moving on to the psychrometric chart. This is a cooling tower psychrometric chart. The x-axis is dry bulb temp, which is in units of Fahrenheit, and the y-axis is specific humidity, which is pound mass of moisture per pound mass of dry air, so just a ratio. The air enters at point A. The heat and moisture goes and exits to point B. So like I said the process earlier, when the heat and the air interact, that's whenever it goes there, and that's the heat transfer, entering to leaving wet bulb temperature. Now, before I move further into the analysis, I want to explain sensible versus latent heat. Sensible heat is the increase in heat as an object's temperature is increased. So it's more of a dependent variable. As the temperature of something's increased, what's the resultant change in heat? Increase. Latent heat is heat that causes a change of phase of a substance, and it can be by addition or removal of heat. So if something changes from solid to liquid, liquid to gas, or something else, that's basically to understand latent heat. Looking at the psychrometric further, A to C is sensible heat transfer. So sensible, like I said, is the dependent. So as the temperature of an object changes, that resulting change in heat. B to C is the latent heat transfer. So the change of phase, heat addition or removal. D to B is the total heat transfer. D to E is the sensible air cooling. E to B is the latent heating when water loses mass and heat to air. So whenever the whole thing interacts, that's the latent heat, the change of phase, whenever that's happening. And the main way I found to understand this was looking at the rate of evaporation from comparing D to B points from A to B, the points. And the evaporation rate of D to B is greater because that vertical change, the latent heat, which is the determining factor, is a higher portion of that total heat transfer than A to B. Moving on, I want to talk about the approach and the range, which are two main parameters of cooling towers in addition to the wet bulb temperature. The approach is the difference in temperature of the cool water leaving the tower and the wet bulb temperature. It's usually about 5 to 7 degrees Fahrenheit. You want a smaller amount, that's better. And the reason you want it smaller is because say it gets to like 10 degrees and it really gets really cold, that means more pressure differences, more losses and friction losses. You don't want too much pressure difference. You want a constant good value, and that smaller approach is better. It's affected by wet bulb temperature and heat load. So heat load, like I mentioned earlier, is basically the quantity of heat removed by the cooling tower. Range is defined as the difference between the temperature of the cool water leaving the tower and the hot water entering it. So 10 to 15 is about what it is. So if the cooling tower cools the water, it comes out at 70 degrees Fahrenheit. That means after it runs through the buildings, the systems, cools what it needs to, it'll come back into the tower at about 80 to 85 degrees Fahrenheit. It's affected by heat load and water circulation rate. And water circulation rate affects this because that changes the flow rate, which then changes the range. A higher flow rate will dictate the temperature more. Part load efficiency, I'm going to talk about next. And basically, the best way I understand this is when you design something, it has to be able to withstand maximum conditions. So, average normal temperature, 70 degrees Fahrenheit. Well, that HVAC system needs to be able to handle 120 degrees and 20 degrees. But the problem is you don't want it to be able to operate solely at its maximum capacity on the extreme sides of the spectrum all the time, because you get so many energy losses. It's going to increase maintenance, it's going to cost more, all these things. So the main upgrade is a variable flow system, and this basically allows you to change the flow as the load changes and as the what the temperature is and what the system needs. So if it's 80 degrees outside, I don't want it operating as if it's 120 degrees. You're going to lose too much energy. So I have an example of a system here. Don't look too much at the numbers. The main point I want to get across is you have 4 cooling tower cells at 75% speed, and this is compared to if you had 3 at 100% speed. And the 4 at 75% speed is better because it's more efficient. It puts less total stress on the system, and it's more cost effective. So this system, this variable flow, is starting to be used more nowadays. So looking at the material it's made of, metal and fiberglass has been used for the longest time, but they're very susceptible to corrosion and leakage. Nowadays it's more engineered plastic. So like this picture here is high density polyethylene cooling tower. It's commonly used. It's reliable, it's strong, it's flexible, and it gets the job done. So lastly, I just wanted to touch on Legionella. Um, it's a bacteria found in warm water, and cooling towers are susceptible to this because there's a lot of warm water open to the atmosphere. And to prevent it, you want to maintain the water source temperature. You want to use disinfectant, just keep everything clean. Any questions? And here are my sources.